He will tell us about counting black holes as algebraic varieties. Abhishek.
Yeah. So thank you, Sarthak, and thanks to all the organizers for putting together a very diverse conference and giving chance to different kinds of talks. And it's also good to be back here at ICTS after 9 long years. I was there for the 2015 inauguration, and then this is the second time I'm here. So today I'm going to talk about counting black holes as algebraic varieties. So mostly here I will focus about zero-dimensional varieties, that is collection of points, but some of the techniques, of course, can also be applied to higher dimensional varieties. And this is a work that I did with my PhD student, Saurav Maji, who is there. And the title of the paper is, of course, Counting n equal to 8 black holes as algebraic varieties. So I will begin with a brief overview of why this microstate counting business is important in string theory and also in the context of black holes. And then I will give an overview of the system that we are using, that is a intersecting D-brane system. And then I will quickly move into the actual talk, which is how to basically solve for supersymmetric ground states in this kind of system using various techniques from mostly computational algebraic geometry. Okay, so the main highlight is this Hilbert series, which is quite general. And I will focus some amount of time discussing the Hilbert series, and then we'll move to some other numerical strategies, which is this homotopy continuation and monodromy. But the Hilbert series is actually symbolically exact. So this is not really a numerical technique, but it is kind of exact technique. And then I will, of course, end with the outlook and some open things that are still yet to be worked out. So yeah, so this has been the theme for theoretical physics for over the last 3 decades. So mathematicians are increasingly getting interested into Feynman diagram as graphs, and then we physicists are mostly getting interested into Riemann surfaces and etc. As physicists. Okay. So here are the main references. So the first 2 papers I wrote with Ashok and Swapnamoy and Richard towards the end of my PhD at HRI. And these 2 papers essentially dealt a lot with how to essentially write down the Lagrangian in this intersecting D-brane picture and working out what should be the Susi ground states and etc. So I will not focus too much on how the Lagrangian came and the setup of the problem. So the main thing is essentially how to solve for the ground states, and that is the focus of this talk. And then there are many other references for n equal to 8 for Ashok, and then supersymmetry for U10. And then this D0, D4 is one of the crucial, Justin's paper is one crucial references here. And then these are all references where these are various computational algebraic techniques. So this is a very good book by Cox on introduction on the computational algebraic geometry, but it still doesn't discuss any of these techniques, but it is still a good building block to get to the notations and ideas of the subject. And then there are other references which are actually the techniques and various papers as recent as 2022 in maths. So it's fairly recent. Okay, so I will begin with an overview of the microstate counting program. So I do not have to tell this audience about why black holes have entropy and other things, but anyway, so we have black holes which have entropy, and we know that this black hole entropy is the black hole area, and then we also know that there are various kinds of alpha prime corrections, then loop corrections, GS corrections, and etc. But the main point is, what is the statistical interpretation of this large entropy that we are evaluating in various kinds of black holes? So what is this omega, big omega, essentially? So this cannot come from the classical black holes alone, because if you fix the mass and charges for a classical black hole, there is almost nothing you can do. It is more or less unique. So any microscopic theory of quantum gravity should, among other things, provide for these microstates. And these quantum black holes, of course, must have these microstates, which should explain this entropy. And string theory, we have an answer in various settings with high enough supersymmetry. We can actually do a very high precision calculation of what this omega should be. And in cases in which we are able to do this computation, things match. So what is there are two pictures that people usually we talk about in this black hole microstate counting business. One is this macroscopic side, which is essentially the black hole side, which is the classical regime in which the gravity is switched on, okay? And the GS has some value. It should not be written as strong coupling. It is strong compared to whatever the value is in the microscopic side. And then in the microscopic side, we have this system of some kind of intersecting D-branes. And this is basically the full quantum regime. There are D-branes, and then there are strings fluctuating on these D-branes. And that provides for various kinds of states. And this is the states that you are supposed to count. And so pictorially, this is more or less the picture. So this is the famous D1, D5 system. There will be strings like this ending on the branes. There can be strings starting on D1 and ending on D5. So some picture like this. There will be strings on two different branes. There could be strings coming from the same brane and ending on the same brane and things like that. And yeah, and when you basically tune the coupling, GS, and then you basically, this picture basically effectively becomes a picture of a black hole. So this is the setup that we have. We call this side the microscopic side. This is the macroscopic side. So the goal, of course, is to compare these two regimes. And to do that, we will focus mainly on the extremal and stable black holes with zero temperature and so on. And they are also supersymmetric black holes. So they are what are known as the BPS black holes. And then you can compute something called the Witten index or the BPS index. And this Witten index is supposed to be protected as we change this coupling GS. And then you can compute this on both sides, on the microscopic side and also on the macroscopic side, and then compare. It's supposed to match. So in certain conditions of positivity and signs and other things, which I will not go into much detail, this BPS index actually becomes the black hole entropy. And this has been an important problem over the last 2 decades. And for a wide class of n equal to 4, n equal to 8 supersymmetric string theories, and some partially for n equal to 2 theories, this microscopic counting has been done in various settings. And whenever we are able to do it, it matches with the macroscopic setting. So the ultimate goal for our picture is to basically do some kind of counting in the n equal to 2 black holes. So these black holes are black holes which you will get if you compactify the 10-dimensional string theory on a Calabi-Yau. Now on a Calabi-Yau, because there are no one cycles, the charges for these black holes can only come from pure D-branes. Okay, so that is the motivation of essentially dealing with pure D-branes directly in the counting. And this is a fairly difficult problem to do at first. So you do a much easier, at least known problem, which is the 1,8 BPS black hole in n equal to 8 theory, because this is a problem which we know how to count. We have counted this in this relatively famous D1, D5 KK monopole P system. So we know that the full generator of the entropies, this comes as a weak Jacobi form. So we know everything more or less as far as the counting goes, we know exactly what this is. But we have, of course, not done it in the pure D-brane setting. This was done in a D1, D5 KK monopole setting, which you can then basically do some U dualities, basically T duality and some S dualities to bring it to a system which is pure D-branes, which we will basically look into. So for the smallest charges, the Abelian charges, so these black holes are 4 charged black holes in D equal to 4 dimensions. So for the smallest charges, which is like 1, 1, 1, 1, this is achieved, of course, in the previous papers. And for large charges, for the non-Abelian case, partial results are now achieved. Earlier also we have achieved some result, but in this new paper we have extended this. non-Abelian case. So in this only 4 supercharges. So 1/8 in n equal to 8, so 4 supercharges. Yeah, so the idea is that once you are able to do this more or less fully, then you can use the intuition to do some other things like K3, which will be some T4 mod Z2, and then maybe if you are managed to do that, then you can go to some simple Calabi-Yau's and so on.
What do you mean by non-Abelian charges?
So, okay, so I will come to this. So basically we have D-branes, right? So these D-branes carry some UN group, right? So if n is 1 there, it is U1, so that is abelian. If n is 2, for example, it is U2. So if you have two D-branes.
But you have black hole solutions with the non-Abelian gauge field turned on outside?
Yeah, so the gauge fields on the D-branes, yeah, so non-Abelian gauge field turns on outside from the macroscopic picture. Yeah.
The closed string description doesn't have any non-Abelian.
No, so these charges, if you basically say that the charge is 2, that means it is a U2 theory in the D-brane, right? So that is non-Abelian in that case.
But your charge is the U1 part of it, or is it non-Abelian? Are they?
Yeah.
Yeah. Yeah.
Only in the D-branes. Yeah.
Okay, so then when you map it to the corresponding black hole, you only map the Abelian charges, which are
RR charges. Yeah. Okay, so, right. So the basic problem of counting this Witten index on this intersecting D-brane system boils down to counting the number of solutions of some matrix equation up to some these GL N1 kinds of identification. So these are basically the complexified versions of the UNs that we have on the D-branes. So we have 4 charges, we have 4 D-branes, and the complexified version of them, all the UN1 will be GLN1. And you have to basically find the number of solutions up to this gauge transformation. And if, I will just flash a result, is that what we find is that if you basically do this counting at a general point in the moduli space, so in here the moduli essentially are, so we are basically doing a T6 compactification. So the moduli here will be switching on some constant B mu nu field, G mu nu fields in the T6. So if you switch that on, then we find that all these microstates that basically carry 0 angular momentum. Okay, so this is different from the previous countings, where of course the counting was not done in a generic point, and then you of course get all kinds of states and they cancel and in the index and then give you the correct answer. But here you actually get what you want. You actually get point by point, you get the solutions, the microstates.
So of course, as far as the superpotential is concerned, you can consider the complexified gauge transformations.
Yeah.
But you also have D terms, right?
That D terms essentially is what is responsible for complexifying this. So yeah, so you essentially have the UN gauge groups, and then the D terms, if you do not want to consider the D terms, you can effectively think that the D terms is automatically satisfied if you complexify the gauge groups.
Any solution
Yeah,
to the
yeah.
superpotential the F-term
Conditions and with the complexified gauge fields will be also, yeah, will be in the orbit of the D fields also. Yeah. Automatically satisfy. Not automatically satisfy, you have to still gauge transform it, but it will, there you can find a solution which will satisfy the D terms, essentially. Yeah. Yeah. Okay, so it has interesting consequences for the fuzzball program, of course, because in the fuzzball, then you basically have to find solutions which carry, in the fuzzball program, the microstates are basically thought of as some mini black holes, but then these black holes should also carry 0 angular momentum, which is apparently very hard to find in this program. Okay, so let me go to the setup quickly. So we have these 4 D-branes. So here I have a D2, D2, D2. These are compactified on the 4, 5, 6, 7, 8, 9 of the T6 torus. And of course, 0, 1, 2, 3 are the non-compactified direction. And then there is a D6, which is on 4, 5, 6, 7, 8, 9. So this can be some N1, N2, N3, N4, but I will be looking at 1, 1, 1, N. And I will discuss a little bit later the other things. And even for setting up the problem, I will even take this N to be 1. But of course, in the papers, we have taken N to be 2, 3, 4, and other things. Okay, so what we have to do is to basically calculate the Witten index of this given brane system. So there is the effective theory that lives on this intersecting D-brane. So we have to calculate the Witten index for that effective theory. So we can only, because it is a Witten index that we are supposed to calculate, we can only concentrate on the very low-lying zero modes of this theory. We do not have to take the full tower of KK modes and etc. We can just look at the low-lying zero modes and then compute this Witten index on this supersymmetric quantum mechanics with a superpotential that we'll discuss what it is. And then the question is to how to build this supersymmetric quantum mechanics on these intersecting D-branes. So to do that, we have to calculate the open string spectrum on this D-brane background. I will not go into detail of how to do all these things. We have details are done 5, 6 years back. But I will just mention that you can calculate the open string spectrum and arrange them in the proper SUSY multiplets. And SUSY most of the time will dictate the interactions that are going to happen between various fields in this D-brane background. And then this Witten index basically becomes the Euler characteristics of a vacuum manifold. Okay, so this is what we really want to figure out. So we have to calculate this Euler number of this vacuum manifold, and in general, this SUSY vacuum manifold will have a structure of some, will be basically spanned by some fields, phi and phi daggers, up to the F term going to 0 and the D term going to 0 to maintain supersymmetry. Modulo, of course, the gauge transformations that we have. So if you do not do this modulo, then of course you have infinite number of solutions. So that we do not want. You of course have to mod it out by the gauge invariance in the system. So the field content roughly is as follows. In the when the strings are ending on the same brane, you have this n equal to 1 multiplets. You have a n equal to 1 multiplets. This is a gauge multiplet. This is the gauge field, and there are these scalar complex scalars, 3 complex scalars, and they are in the UN representation, adjoint UN representation of the UN gauge group. And then there are these strings which are ending on one D2, another ending on another D2, and they basically gives you fundamental and anti-fundamental fields, which are basically the Zijs and Zji. So it's like 1, 2, 2, 1, and so on, all combinations for the branes like this. So this is more or less the picture of the field content. There are various interpretations that you can give to the various coordinates. Let me not go into this. So basic intuition to build up the Lagrangian would be that because these branes are kind of only seeing, it has only 2 endpoints, either it can end on the same brane or it can basically end on 2 different branes. So the full Lagrangian will be a sum of pairwise interactions mostly. Okay, so and then these mixed strings which are going from one brane to the another brane, which is Z12 and Z21, they should talk to the gap between the 2 branes. So these V1, V2 and R1, R2 are basically the coordinate gap between the D branes, and they should talk only with the gap and not the absolute values of the V1 and V2. So the other combination, for example, R1 plus R2, will turn out that all those things will not appear in the Lagrangian, and for a good reason, because they are all the Goldstone modes. So this D-brane has a lot of Goldstone modes. You can basically slide one brane across another and then slide the full system. And so there are various Goldstone modes, 28 to be precise. And you have to basically take out, so this Goldstone mode should not come to the Lagrangian, because this is not what we are interested in. We are interested in the microset counting of the black hole itself and not really the movement of the black hole. So that part you have to basically mod out. So of course, we have to mod out the Goldstone modes. And because we still have 4 supercharges, this Goldstone, of course, has Goldstinos, which essentially are the broken SUSI. So we have 28 broken SUSI. We started with 32, 4 is preserved, and 28 is broken. So these 28 broken SUSIs are basically the Goldstinos. So roughly the Lagrangian will look something like this. So there is a n equal to 4 super Yang-Mills Lagrangian for each brane. This is appropriately compactified because the actual theory that we have is basically a quantum mechanics, because the intersection of the branes is only common direction in the intersection of branes is the time. So it is a quantum mechanics. So you have to appropriately compactify. But the field content is of the n equal to 4 super Yang-Mills. And then there is this pairwise interactions which give you a n equal to 2 theory. And then there is this superpotential that we sort of add by hand. Some part of it is, of course, not added by hand. For example, this n equal to 4 part, though this Wn1, of course, is added by hand, but this n equal to 4 also will have superpotential, like this phi commutator, phi 1 commutator, phi 2 commutator, phi 3 kind of superpotential that we have in the n equal to 4 super Yang-Mills. And then there is this Z phi Z kind of Yukawa kind of couplings that we have for the n equal to 2. And this is the part that we had added by hand, sort of. So there are signs which are quite important apparently. And then there is this Z, Z, Z. So this Z, Z, Z essentially signifies a 3-brane interaction. So a string is coming from first brane to second brane to third brane, and then again going from the third to first. Okay, and then there are some other fields, this R1 minus R2. So these are basically responsible for giving masses to these Zs, okay, and also making sure that the Zs do not vanish in the supersymmetric vacuum.
Is coefficient C, right?
Yeah, I will come to that.
Yeah, so it's not that we had it by hand.
No. Yeah, it's not totally by hand. But of course, the ZZ, the signs are by, yeah, so everything is calculated. So I will just, the next slide is there. Yeah. So let me just come to a bit more detail. So we, of course, computed, as Ashok mentioned, that this C. So this C can be computed by doing a 3-string amplitude, okay? And it comes out to be up to plus minus 1. If you basically take all the cocycle factors, etc., it should give you the exact signs. But we didn't need the exact signs because there is some other discrete symmetries, which is like interchanging the branes itself, that fixed all the relative signs for us. So otherwise, we would have had to do the calculation more exactly. But yeah, so we fixed this C to be plus minus 1, but and the relative signs here are basically fixed by some discrete exchange symmetries. Okay? And then we have this W2 part, which is this some C12, this phi 1 3 minus phi 2 3. So this basically this C12 is basically is appearing because we have switched on background B mu nu field and G mu nu fields in the T6. So T6 is not really perpendicular. So there is a G mu nu and B mu nu switched on in the T6 direction, and that is responsible for basically creating these C12s. C12s will be functions of those G mu nus and B mu nus that we have switched on. That switching on also creates the Fi parameters, okay, and those things are also responsible collectively for these mixed strings, these Zs, to not vanish at the vacuum. Yeah, so there could be higher terms in W, but you can basically show by a scaling argument that they are very suppressed. Yeah. So I think if you scale these Zs by some lambda, then that will basically, the order of lambda will change here if lambda is a small quantity. So basically what we have done is that we have taken that this difference between phi 1 and these are basically the coordinate differences. So these coordinate differences are small. So if I take that scaling and then put it to Zs, we can show that the ZZ term will be parametrically smaller than this ZZ. But in our paper, I don't know how much it is correct. I have actually taken the ZZ term and then kind of showed that this is incompatible with these discrete symmetries. But it probably is not very correct because I have to cannot stop at ZZZ, but I have to basically take the full thing then. So ZZZ and all the higher terms. But I have checked up to some more higher terms, and all of them are basically ruled out by these discrete exchange symmetries, but I'm not very sure about that. But in any case, yeah. Linear in the files. Yeah. Yeah. Okay, so if you do these calculations in the abelian case, you basically get this, as I was mentioning, the D-term equations can be thought of as complexifying the gauge symmetries. Then you get these 12 Zs, and there's 3 complexified gauge symmetries. One of the gauge symmetry, of course, there are 4 U1s, but one of the U1 is the overall motion of the D-brane system or the overall motion of the black hole, which you have to mod out by. And then you can create these gauge invariant combinations, Z12, Z21s, and so on. So these are all gauge invariant combinations, and these are actually coming from the F terms. So if you solve this for these abelian cases, which is charge 1, 1, 1, 1, then you get the solution 12. Which is correct, huh? Which is W prime? Yeah, so these F terms are basically del W, del phi, del W, del Z, putting to 0. Yeah, so this is not the directly, these 3 are not directly the F terms. So F terms are many more, so we have basically substituted. So there are many F terms which we could combine to basically make this cubic.
Satisfy these gauge invariant equations.
Right.
Which of course have the complexified gauge.
Right.
Then you automatically find the solution.
Not automatically. So we'll not automatically find a solution, but we can then move in the gauge orbit and then find a solution for the data. Yeah. Yeah, complex ideas. Yeah, so the natural attempt, of course, would be to, in the non-abelian cases, also do it in the same way. So here we have done it in a gauge invariant fashion. So we have basically all these combinations that we have are gauge invariant. So natural thing would be to also do this kind of things in the non-abelian case, but of course this is quite difficult because here in the non-abelian cases, typically you have many more number of these gauge invariant combinations than you should actually have. So basically they will come as, there will be more generators for this. If you think of this as coordinates, if you think of these gauge invariant things as coordinates, then you will have many more coordinates, and then for the extra coordinates, you will have extra constant relations, which are known as syzygies, and then you are never sure when this is going to end. So there are many more generators than you should expect, and then to compensate that, there are many more constant relations, and this keeps on going. You never know where it ends. So directly changing the non-abelian system to a gauge invariant system like this, where you have to solve these polynomial equations, we are not able to do that. I don't know whether, I don't think there is a very straightforward way of doing this. So what we do is to basically take help of certain other techniques to extract this gauge invariant part from the non-abelian cases. So there are 2 kinds of things you can do. One is that you can not think about gauge invariance. You can actually gauge fix the system. And when you gauge fix the system, then you basically can use these methods, this homotopy continuation, monodropy, and Hilbert series itself to basically solve this kind of polynomial equations. Of course, some of the z's will be set to 1, some of the z's will be set to 0 because of the setting of the gauge fixing, but you can solve it in some case, and we have solved it by gauge fixing. In 1112 case, it is 56. In 113, it is 208. 114, this is 684, and we are able to do some more higher charges, but all this matches with the U-dual degeneracies that we have from the D1, D5 KK monopole system. So I will come to, as I don't know how much time will be there, but I will come to some of these techniques later on. But let me focus more on the gauge invariant way of extracting the number of solutions, which is basically done by this symbolically exact Hilbert series method.
Sorry, just naive question. So in the KK monopole description, these degeneracies are known exactly for finite n. Even
Actually, for all charges.
For all charges, it is known.
Yeah.
And what is the, you said in the beginning, but I didn't get, what is the motivation for going to this pure D-brane system?
This is to basically actually deal with n equal to 2 black holes. So if you basically have string theory compactified on Calabi-Yau's, then Calabi-Yau's do not have one cycles, right? So there cannot be a momentum running on this one cycle, which is typically there in this KK monopole D-brane system, right? So you cannot have this. So all the charges have to be from the D-branes in the n equal to 2 setting.
This D-brane setting that you have, the large n limit is already known. Is that easy to get or?
No.
So even the asymptotic formula is not, you don't know?
Yeah, it's case by case studies so far, yeah. Yeah, there everything is known. There the asymptotics is also known.
A theta function, right? Inverse theta function, and you can expand.
Basically, yeah, theta square divided by eta tau to the power 6.
Yeah. Because this is just 108 BPS black holes in n equal to 8 supersymmetric.
Just the, there everything is known. Even all charges are known, asymptotics are known, everything is known.
Then
it is not known. This is the, what we are doing is the pure driven description. So here it is, of course, so far it is case by case. Of course, we want to know this. That is the hope. Okay, so I will focus a bit on this gauge invariant Hilbert series methods. Okay. So let me just give a very short introduction to this algebraic geometry. So the only thing that we need is basically what is a polynomial ring. So if we have variables x1 to xn, then the set of all polynomials are basically a ring. And then you can basically have certain polynomials, this f1 to fk, these are like our f terms. And then you can basically create what is known as an ideal. So these EIs themselves can be polynomials. So this is a set of a lot of polynomials in some sense. Is generated by this f1 to fk. Then you can think of this coordinate ring, which is this affine variety space Vf, where you basically set this f1 to fk to 0. So if you set this f1 to fk to 0, this is like setting the f terms to 0 for us. This creates a affine variety, a space. In our case, this is a lot simpler thing. It is basically just a collection of points, but in general, it defines the affine variety. Okay, and then this affine variety is basically called a coordinate ring. Okay, so this is basically coming from this ideal. So this ring is essentially, you can create another R of Vf, which is basically the coordinate ring for this affine space Vf by basically taking the original polynomial space and then modding out by this ideal. Okay, so the thing is that this is algebraic, this is more geometric, and the main lesson from algebraic geometry is that, of course, these rings are Vfs knows about this affine space Vf.
In our case, you have a collection of points.
Yeah.
That's not proven, right? I mean, we are hoping that it will be a collection of points. Sorry.
Yeah, so we find that it is a collection of points, but so yeah,
in the cases that we have studied,
that we have studied,
in general, it is not proven, right?
It is not true, and I will basically mention this at the end.
So you are saying it is not true also, or it is true but not proven, or it may be true but not proven.
Yeah, so these techniques are of course much more general than collection of points. This is completely general. Yeah, so for the cases we have done, we have always found a collection of points, and the numerical techniques, this homotopy continuation, monodromy, etc., only works for collection of points. They cannot be lifted to general curves or any other kind of varieties. But Hilbert series is much more general. They can be lifted to other things also.
Okay.
The number of conditions and the number of variables, are they equal, or is Is it overdetermined? Just as a zeroth order?
Yeah, so you can make it as what we call a square system. So number of variables, after you gauge fix and do all these things, you will see that the number of polynomials and the number of variables are same.
But of course, still,
Yeah,
you could have
we could have a, yeah, so that doesn't guarantee, because this is multivariable things, so that doesn't guarantee. Okay. So in the Abelian case, we definitely use this strategy, sort of, not really mentioning it, but we did use this strategy, and basically we took these coordinates to be the gauge invariant combinations and so on, and basically solved the F-term equations. But as I mentioned, this is not easy, because it is not easy in the non-Abelian case to basically, if you go to the non-Abelian case, it's not easy to find this structure of this RVF very easily. So what we'll do is basically move to a slightly newer strategies.
just one more quick follow. When you found in the explicit cases you worked out only discrete points.
Yeah.
Was that for a generic point in
Moduli space, yes, that is the thing. So if you are counting this in a generic point in moduli space, we expect it that we will get the actual black hole microstates, which will carry zero angular momentum. And then we can argue that because they carry zero angular momentum, they have to be set of points. But then if you kind of calculate it in special points in the moduli space, that is what the original calculation of D1, D5 KK monopole P system was. Most of the moduli are set to zero. That's it, like a special point in the moduli space. When you do this counting, then of course you get full towers of angular momentum states, both bosonic, fermionic, and they cancel, and then they give out a number, which is again the black hole entropy. Yeah. Okay, so just to give a flavor of what is the difficulty. So suppose you just have this 3-node quiver example. So basically means you have 3 U1 gauge fields, and then there are bifundamentals running between these U1 gauge fields. And if you basically create the gauge invariant combinations, so naively, these are the gauge invariant combinations that you can create, this x1, x2, x3, x4, and x5 out of this. So I am not even talking about F term here. So just from this fact that you can naively create these gauge invariant combinations, you see that these x1 to x5 are not independent of each other. So there is a syzygy or a relation between them, which is x1, x2, x3 is equal to x4, x5. So the actual coordinate ring, even without F term or anything, and even without any superpotential, the actual coordinate ring is not just the polynomial space spanned by x1, x2, x3, x4, x5, but this modulo this ideal, which is this constraint. Okay, so even before F term, there is problems like this in basically figuring out what are the actual combinations of the gauge invariant combinations that you should basically look into. So in the non-Abelian case, of course, this is a genuine problem. So many times you figure out a new gauge invariant combination, you have to check that whether it is independent or not. And if you basically see that no, it is not independent, it is dependent, then many times you will see that it is dependent non-polynomially with the other ones, because here I could have said that I am substituting x as x4, x5 divided by x2 by x3. That will be a non-polynomial relation, which we do not want. And then in the dependent cases, that you have to add the new gauge invariant combination and also add a new syzygy to compensate for this. And this can go on forever. So the new strategy that we can employ is to not start with this gauge invariant combination to start with. So we have the polynomial ring, and we start with the basic variables, that is the Z12, Z21s, and etc. They are not gauge invariant. You start with the basic variables and then impose the F term equation as an ideal on this ring and compute the quotient ring R modulo I, and then try to extract the gauge invariant part from this quotient module that we have, R mod I. Okay. And if you manage to extract the gauge invariant part from this ring, quotient ring, that will basically be the coordinate ring of the vacuum moduli space. Okay. So we are not starting from the beginning with the gauge invariant variables. We are doing that at the end. We are just extracting it at the end, the gauge invariant part, after doing all the calculation. So the tool that you use to do this is the Hilbert series. And then there are computational algorithms are basically in Macaulay singular, and we also tinker around a lot, making some private modifications, etc. So what is this Hilbert series that we have? So it is basically a graded ring. Okay. So the best way to see is maybe something like this. So suppose you have these two variables x1 and x2 in C. So if I basically assign a charge 1 to this x1 and also a charge 1 to this x2, such that x1 square will be charge 2, x2 cube will be charge 3, and so on. This is basically counting the degrees. If you think of the degree as a charge, then at level n, you basically have all these monomials. Is x1 to the power n, x1 to the power n minus 1 into x2, and so on up to x2 to the power n. So then you can say that at level n, the space, there is a vector space Vk which is spanned by all these monomials. So there are exactly k plus 1 of them for hk. Okay, and the Hilbert series can be thought of as a generating function for this dimension of these vector spaces at each charge level k. Okay, so this T can be thought of as a chemical potential. So this is very much like a kind of partition function calculation. Okay. So this charge assignment here, I have only taken the charge to be the degree here, but of course we have gauge symmetries, so I will assign charges for the gauge symmetries also. So this is just what is.
So I have said x1 has charge 1 and x plus charge 2.
Yeah, that I can do. Yeah, I don't think there will be much problem there. Yeah.
But they'll give a
As long
different
as these are
series.
positive charges, I think. There is a positivity conditions and other things there, but as long as that is, yeah. So, yeah, but with this has a nice form, because this kind of, this form 1 divided by 1 minus t square basically this 2 basically tells you that this is a 2-dimensional space. So yeah, that assignment will probably change a little bit if I basically tinker with the charge assignments. Okay, so of course we do not just have the degree of the polynomials, we also have to keep in track.
So this is somehow the order of the pole as t goes to 1, is that right? The dimension will be.
Yeah, order of the pole as t, if the variety is a d-dimensional variety. So here, of course, it is a 2-dimensional variety, right?
Yeah.
Spanned by x1 and x2.
Okay.
So that information is here.
I see.
Yeah. So in the Abelian cases, of course, you can do this, and also for the non-Abelian cases. So what we have to do is to generalize this. So instead of just having one charge like the degree charge, you also have gauge symmetry. So put the U1 gauge charges for this gauge symmetries also, and basically build what is known as a multigraded Hilbert series. So there will be grading not only because of T, which is the degree charge, but because of Z, which are basically coming from the gauge. So we have 3 gauge symmetries, 3 these relative U1s. And in the non-Abelian case also, you can take the charges of the U1s from that UN and basically give it the charge, give this charge. And if you do that, it turns out that you can evaluate this exactly. And then what you want is to basically extract the gauge invariant part from this Hilbert series. So that basically the gauge charges are carried by this Z. So what we basically want is in all this expansion, what is the n equal to 0 term? Okay, so that you can extract, and if you extract that, that basically forms the ring of invariants. Now for a 0-dimensional varieties, we have another thing, which basically is that this ring of invariance, if we extract the Hilbert series, will look something like this. Z-independent Hilbert series will look something like this. But for our case, this D is also 0, because what we find is in most of the cases it is 0-dimensional variety. So then if you put this t to be 1, it actually counts the number of points. So there are theorems and etc. doing this. I'm not going into this, but yeah, for 0-dimensional varieties, this will exactly, if you put h1 for t equal to 1, it will just count the number of points. Okay, so in the 2-node QVAR, in another toy example with only 2 fields, Z1 to Z21, only gauge invariant combination is 1, 2, 2, 1. So if I have a F term like this, Z1 to 2, 1 minus 1 and Z1 to 2, 2, 1 plus 1 equal to 0, the only, this if you solve it, there are only 2 points, right? Gauge invariant 2 points. So if you do it by the Hilbert series way, you assign a U1 charge to Z12 as 1, and you assign a U1 charge Z21 as -1. And this is sort of a bookkeeping charge, which is keeping track of the degrees. And then the ideal is basically this F-term equation, which is this. And you can then form the quotient ring, which is this R mod ideal. And for this quotient ring, it is possible to calculate the Hilbert series. It will come out something like this. So these parts are easy to understand. This is just like the bosonic oscillator with charge Zt, and another one was the 1 over Z charge, and then T. T is the degree and Z is the gauge charge. And this T to the power 4 minus T to the power 4 is signifying the fact that you have a order 4 or degree 4 constraint on like this. This is a constraint, right? You have a order degree 4 constraint like this. So this information comes out as the minus sign here. Okay. And if you basically try to extract the Z invariant part, it will come out to be 1 plus T square. And if you put T equal to 1, it is coming out to be 2, and we get the correct counting. So of course, this can be done for the Abelian case. Let me skip. It is more or less the more charges, more things. But yeah, so the main thing is the Hilbert series can be counted. There are more gauge charges now because there are 3 relative U1s. So T0, T1, T2, and there is this bookkeeping T3. And then if you calculate the Hilbert series, the numerator is a very long thing. It's a much simpler denominator. And to basically extract out the gauge invariant part, you have to basically get rid of the T0, T1, T2 dependence from this Hilbert series. So that you can do by doing a contour integral appropriately. And then finally, you will get the H as a function of T3, which is the bookkeeping charge, or the degree charge. And if you put H1, it gives 12. So this, of course, again matches. So for the non-Abelian case, the story will be more or less same. Only thing is that because this global charge or the bookkeeping charge commute with the gauge charge, these things commute, and this non-Abelian part of the gauge symmetry will come as a character in this Z. Okay, and then to basically extract the Z invariant part, you have to basically use the Weil integral formula and do a Harmager integral like this on the Hilbert series. And again, you will get some gauge invariant Hilbert series. So for example, in the 1, 1, 1, 2 case, for the SU2 case, the Harmager is something like this for the SU2. And if you put the field contents and you do the contour integrals and etc., you get 56, which is again the correct answer. So you can keep on doing this, but only thing is that for higher and higher charges, the number of fields scales exponentially. So the computational power, mostly RAM kinds of shoots off. So I only have 128 GB. So this, yeah, I more or less could do only this up to, if I basically just focus on the gauge invariant part. So let me just quickly move to other strategies. So far this is all gauge invariant. Okay, so this is a nice way of figuring, basically extracting the gauge invariant part. But we do not have to do that. There are other strategies where you can gauge fix and then find what are the number of solutions. So one is this homotopy continuation, where if you are given a square system, which is like a system where you have same number of polynomials as variables, then you basically first build an auxiliary system G of X, something like this, which is much simpler to solve. Okay, and once you have solved this, then you basically create something like a homotopy map, which is some parameter Tfx and plus some 1 minus Tgx. Okay, so Gx, the solutions of Gx I know. So what we basically do is to track these solutions along this T and find what are the solutions for f of x. Okay, so this is something that can be done. Yeah, very cleverly, yes. So that is the whole point. So that is why we could not have done all these things when we are writing those papers, because all these things are very recent, 2022 more or less. Yeah, so one way to very cleverly choose the g of x is what is known as total degree homotopy. So basically, these d1 to dk are the degrees of the polynomial f1 to fk, and you just have just one term a1 x1 to the power d minus b1 equal to 0 and things like this. Is very easy to solve, right? But unfortunately, for a lot of, if you have lot of variables, this quickly goes out of hand. Because if you have, for example, in most of the cases, we have d which is 2, and then we have variables like 24 or something. So you have to tag 2 to the power 24, 2 to the power 30, 2 to the power 40 kinds of solutions, which of course goes out of hand. So then there are ways to very cleverly choose what should be the start polynomial and still be able to solve it. So this new things, this polyhedral homotopy. So I will not go into all the details of the algorithms and the math behind it. Yeah, so there is a much more efficient way of choosing this using Newton polytopes and other things from the original system f of x of polynomials. And the advantage, of course, is that the much less number of paths need to be tracked. And this is what we have used for all our calculations in the gauge fixed way. So this tracking can be done by basically converting the whole problem in a set of ODEs. So this hx, so if you are basically knowing the solution of h of g of x, then you can think that this h also has a solution which is parameterized by this t. So for each t, there is a solution for this x. So then you can, if you take a derivative of this, it basically gives you a ODE like this, and this ODE can be then solved with the initial condition that x at 0 is x0, which is basically the solution of g of x. So with this initial condition, you can solve this ODE.
So presumably for this to work, you need the number of solutions of g of x to be larger than
this, yeah. So this is what is made sure by this Newton polytopes.
I see.
So that is inbuilt in this in the math. This polyhedral. Yeah, so they basically transform the original system to a toric variety, and then again run various other things to make that toric variety even a better toric variety, and so on and so forth. But yeah, so yeah, it will miss a lot of solutions. Actually, Saptama have tried that. It misses a lot of solutions. Yeah, these things do not miss much. It's more or less, yeah, it's numerical, but still more or less exact. Yeah, so what will happen is that, as Ashok mentioned, you have more number of solutions in Gx than the Fx. So when you basically are tracking the solutions from Gx to Fx, what will happen is a lot of solutions from this Gx will basically track to infinity. And then you will throw away those solutions, and whatever remains will be the actual solutions of this f of x. Okay, and this works. Okay, let me not skip the example. It's not very good. So for our system, we can of course do some gauge fixing, and you can use the shift symmetries to basically put the system to a square form. It is not, originally it is not in a square form. You can put it in a square form by using this, and then you basically use this new player in town. This is also, so a completely new language was written called Julia by people from MIT, which is much faster for computations like this. And this package was more or less written by them in 2018-19 to basically do this homotopy continuation. So this was not available earlier. And then I also made modifications to this thing to adapt to our cases. And the result is this, more or less. So if you basically start with the Abelian case, 1, 1, 1, 1, you have 15 variables and 15 equations, and there are 16 paths. And of this four of these paths goes to infinity, and then there are 12 solutions as expected. So as you can see, if you increase the charge from 1, 2, 3, 4, the number of paths that need to be tracked is kind of exponentially increasing. And a lot of them, or most of them, will basically diverge to infinity, and only a few finite number of them will be remaining, and those basically give you the correct counts. And this is very, very fast. So 7 years back, we have done this 1113 case in Mathematica. It took, at that time, it took 10 hours. Currently in Mathematica, it takes about 5 hours. With this method, it takes 1 minute. So it is that order of magnitude fast. I can go fairly high. My only limitation is RAM. If I basically give you a little bit of RAM, then yeah, I can go high. Yeah, so there is, okay, I have maybe 5 minutes, so maybe I quickly mention another interesting technique. So this is called a monodromy group action on a variety V.
One thing.
Yeah.
So 1122 is supposed to have the same answer, the 684, right?
1122, but yeah, you are not getting. I will come to this.
I see. Okay.
Yeah. So okay, let me mention this here. So because I invested this time and to do all these things, at least what is clear is that, of course, I can go now up to 1114. That is something. But the more interesting thing is that I can now basically switch on 2 non-Abelian charges. For example, I can do 1122 or 1123 and so on. Interestingly, those things are not matching with the original count. So this is a puzzle that we're trying to solve what is going on. But yeah, so far, so this, if I basically do this non-Abelian thing, only one of the charges things are matching. But if I basically switch on non-Abelian charges on 2 of the charges, then things are not matching, and not matching in a very interesting way that I will come to maybe, yeah. So there is this monodromy technique, which basically what you do is that you take the original system f1 to fk. These are the original polynomials that we had. This should be k, sorry. x1 to xk. And then you basically change it a little bit with some parameter p1 to pk. Now, if you do this, you can of course find a seed solution for this very easily. For any value of p, you can find a solution for this. And then you can basically move in the, or basically make loops in the parameter space. So in the space of this p1 to pk, you basically make loops around some p0. If you make loops around this p0 in the parameter space, you would expect that you will get back to the same solution, but actually you do not get back to the same solution, you get back to different solutions for this set. Okay? So this way, by just making loops in the parameter space p, you can basically map out the full set of solutions for this system, f of xp, and then you can do another homotopy continuation to change from whatever the value of p is there to p equal to 0, which is our system.
I mean, if you keep making loops, at some point you have to decide that you have got.
Yeah, so they basically, there is a check. So they check whether the solution is already available earlier. So there will be, so at some point, there will be checks that they have run 2 or 3 loops and got no new solutions. So then you stop.
I see.
Yeah. Yeah, and this is even faster. So this is about 10 times faster than the previous method. Okay, so this is even faster than this. And many of these things are fast because they completely utilize the parallelizability. So from top to bottom, these codes are parallelizable. So if you scale your computation system, things will scale, which is not the case in Mathematica, of course. Okay, so I will skip this Newton-Polito. Anyway, this doesn't really work for our case, except for the Abelian one. But this is important to basically do the homotopy continuation. But I will just skip it and I'll come to the...
Works up to 1114?
Which one?
The monodromy method.
Yeah.
That works up to 1114, I see.
Okay. So let me come to the last 5 minutes, maybe. So we have this zero angular momentum microstates from all this counting, which Of course, we know that this is something that we should get from the macroscopic description of the black hole, because in the macroscopic side, the near horizon geometry is ADS2 cross S2, and from there, the angular momentum can be thought of as a ADS2 charge. And then because it is ADS2, you have to be in the microcanonical ensemble, so the angular momentum has to be 0. So all the microstates should carry 0 angular momentum. This is not what you find in the typical D-brane kind of calculation. So for example, this is not what you find in the typical D1, D5 KK monopole calculation. There, of course, you will find a lot of states with non-zero angular momentum. They will cancel among themselves, and then they will give you the index, and that index you can think that that is the black hole entropy. But in our case, that is not the case. We are getting exactly what we want. In our case, we are getting actually the microstates. So if I'm getting 12, that basically means we have 12 number of microstates, and I know what are these microstates. There is no cancellation, nothing happening, and all these microstates, of course, carry 0 angular momentum. So this is a much direct approach. Okay. So let me come to the comments.
Since these are not vacuum states, by Witten index, you really mean this helicity trace, right? Or
Helicity trace, B14, yeah.
so that has some 2J3 insertion
yeah, so you have
in the
to soak
ball.
up the normal.
Right, so if it has 0 angular momentum, don't you get 0? Because J3 will be 0 for these.
No.
No.
So you have already soaked up all these multiplets, right? The gravity, the multiplet that is coming from the broken SUSI, you have already soaken up. So once you have soaken up that, what you should get is the genuine microstates of the black hole. Of course, that actually have angular momentum that you have already soaken up.
Yeah, I think in the ADS2 language, the modes that are responsible for saturating this 2J3 to the 14, that is outside the black hole horizon. That's living in the between the horizon and infinity, right? Because these are associated broken SUSI.
Broken SUSI are outside the horizon.
So the horizon captures the part that is that's beyond this zero mode part, essentially.
Okay, so let me just come to the final comments. So of course you can carry on this for other ends. We have done for some few more things matches. There's no surprise there, but the surprise is here. So it can also be possible that if you take n to be large, and as Raghu was pointing out, it might be possible to basically give kind of a asymptotic formula for this, where the CGGs will simplify or so on, but I don't know when it might happen. But what I know is this is now tractable. This I can do now with these new techniques, this making two of the things non-Abelian. And somehow this 1, 1, 2, 2, if I do, the potentials seem to get flat directions. And this I can know because of the Hilbert series calculation. So if I do compute the Hilbert series, I will get a 1 minus t to the power some factor in the denominator, which will basically tell me that the dimension of these spaces are not 0 dimension, but some dimension, which is confusing because it should not be the case.
But sorry, just to ask you, I mean, the coefficients in these superpotential terms and all, they all depend on the closed string moduli, right?
Right.
But even for a genetic value of those moduli,
yeah, this is happening.
you get flat direction.
Yeah, so that is the surprising part. And similarly, for 1, 1, 2, 3, we do not get flat directions. But if I do this, if we run these methods, then we get 3, 5, 8, 4 as the number of solution. Whether from the U-dual picture, you should get 5, 6, 1, 6. Now, this number is a very precise number. This is basically 5, 6, 1, 6 minus 2, 0, 3, 2. And this is the numbers that you will get if you basically compute the counting for the charge 1, 1, 1, 6 and 1, 1, 1, 5. So some kind of, as I also mentioned to Ashok, some numerology is happening. 2 into 3 is 6, and then 2 plus 3 is 5, so something is happening there, I don't know. So this is also something that should not have happened, but it is happening. We don't know why. And of course, then if you basically switch off one of the charges, if you go to a 3-charge system, then potentials are again having flat directions. So there, I was attending this conference in number theory and physics in Trieste in June. So there were a lot of talk about Lagrange programs and modular forms and etc. So the basic motivation there is that you have some modular curves, which is basically getting connected to a modular form. So in our case also, we have this Jacobi form, right? And then the coefficients of those Jacobi forms are basically solutions of a set of equations, which you can think of as an algebraic variety. So in that sense, it kind of falls under a much broader kind of Lagrange thing, but I have talked to mathematicians about this, so they don't seem to agree in the sense that the Lagrange is now very specific. So the Lagrange only works for modular forms of weight 2 and higher. And what we have is these Jacobi forms are basically weights, weight -1 or weight 0, no, -1, sorry, weight -1 and some index. So yeah, so it is not exactly the Lagrange program, but at least on the face of it, it is the same thing. You have a set of equations, which is like algebraic variety connecting to a Jacobi form, which is the dual picture. And of course, you can again, if we manage to do these things, hopefully we will be able to solve some of these things. And then we can basically go to the n equal to 2 black holes, the Calabi-Yau ones. And the intuitions gathered from doing all these things probably will help in doing the n equal to 2 black holes. So that there the hope is that all the integrate details of the cycles and etc. will probably not be useful in the n equal to 2 black holes, because here overall everything is given by the very local descriptions of intersecting branes and the local strings that are fluctuating near the intersection of these branes. So hopefully that picture also will be valid in the n equal to 2 case. Okay, so with this, I will probably end with this last slide. And thank you for attending. And any questions?
Is 111n. How far have you gone in n?
I think 5 or 6 we have gone.
I see, and the results agree.
Yeah.
I see.
Can I just ask a clarification question? So practically when you were using the word non-Abelian, you just meant capital N bigger than 1, right?
Right.
So what was the non-Abelian charge? What were you referring to? I mean, I understand that the gauge theory on the brane is a non-Abelian gauge theory.
Yeah. So that is the charge, right? So for example, if it's a U2 theory, the charge for the D-brane will be 2. So when I'm saying, for example, say for example this 1122, the third brane has charge 2, fourth brane has charge 2. So there is a U2 theory on this D-brane, third brane, and there is a U2 theory on the fourth D-brane.
Usually we don't use the word charge, right? For it's just some gauge group, or maybe I'm just getting confused by the word charge.
From the wall volume perspective, it's a gauge group.
Yeah.
But from the bulk perspective, is the number of units of charge that the D-brane is carrying.
Right. So that I agree. So N is some charge, it will be some charge and some U1 gauge.
Exactly. Yeah. Ramanujan U1 gauge field, which is under which this is charged. Yeah.
You're calling it a non-Abelian charge.
Yeah, it's not non-Abelian charge. I think the gauge group is non-Abelian, or the wall volume theory is non-Abelian, but the charge is abelian. Yeah.
Just a terminology.
Okay. Sorry.
So, yeah. So, sorry, Abhishek, I should know the answer because I've discussed this sort of question with you and Ashok. But so let's say that we have this discrete isolated minima then, and you also have broken some amount of the supersymmetry. So if I just look at the local quantum mechanics, do you have fermionic low energy Goldstein-like modes? I mean, what is the low energy dynamics?
So there is, of course, this broken supersymmetry, that hypermultiplicity is, of course, they are attached to all this each minimum. But that anyway is kind of trivial. That is the Goldstino thing.
Correct. Okay.
Apart from that, there is no fermionic excitations. So there is, for example, no jumping also. These are either all bosonic vacua, or you can label it as fermionic. So the jumping from in SUSY quantum mechanics is always from a bosonic to fermionic. So tunneling and all those things. So there is no tunneling, etc. Nothing will go.
So it's around the sparse number of degrees
Yeah,
of freedom,
yeah.
and then no.
Yeah, I think when you said no fermionic modes, no fermionic zero modes, no further fermionic zero modes.
Zero modes.
But there are non-zero modes certainly, right? Because this is supersymmetric quantum mechanics. So there will be a bosonic harmonic oscillator and their fermionic partners, right?
So
you still have 4 supersymmetries unbroken, right? So it's a quantum mechanics with 4 unbroken supersymmetries. But those are not zero modes. Those will be like fluctuating fermionic modes and bosonic modes around.
That will come in the Lagrangian itself.
Exactly, that will come in the Lagrangian itself. Yeah, when we expand the Lagrangian in this around the minimum, it will automatically come.
And then, sorry, just to understand, so let's say, as you said about the quadratic, about the minimum, it's some quadratic harmonic oscillator. How many species are there? Is it governed by n charges?
How many species?
I mean, of the harmonic oscillator.
I think that's a dimension of the space because you can move in any direction, right? You start with a huge dimensional space and you minimize the potential. And you can go in any of those directions. So that dimension grows very rapidly, I think.
Yeah, that is the main problem with this approach. So that number of fields, which is basically growing very. Each brane you are 6 directions, and then you have the full. If you are increasing the charge on the D-branes, you have the full.
So it's like an exponential.
Exponential increase. Yeah, right.
Okay, thank you.
Okay, let's thank Abhishek for a nice talk.
Okay, thank you.